everybody, and welcome back from our little side detour with visualizations. Now it's time to get into standardization. Let's get into it. Here's our brief overview, of course. We are going to talk about that normal distribution, have a few historical moments. Then we're going to talk about standardizing the numbers with z-scores. We're going to talk briefly about the 68, 95, 99 rule. Then we're going to see how z-scores, percentiles, and probability all work together. And we'll have a quick moment for z-scores in R. So let's carry on, everyone. Carry on. Here is our normal distribution again, this beautiful, nice curve. This is also called the Gaussian curve, and it's time for 2 historical moments. Our first figure for our historical moment is Johann Carl Friedrich Gauss, or just Carl Gauss. Carl Gauss was a German mathematician and physicist born to a poor, illiterate, working-class family. They didn't even actually know his birth date. They did not actually record it, but he was able to figure it out based on a few key details they gave him. Lore has it that one time he was in class, and even at a young age he was very bright, and a teacher noticed he wasn't paying attention, so the teacher punished him by making him sum all the numbers 1 through 100, and thinking that would be proper punishment and keep him busy for a while. He solved it immediately, and the answer being 5,050, because he quickly noticed that if you take 1 plus 100, so the 2 on the outside, 1 plus 100 equals 101, and 2 plus 99 equals 101, and you do that all the way through, you have 50 101s, so you just multiply that and you get 50-50. I'm sure the teacher was not amused. But that was just showing how precocious he was, even as a young child. His life was dedicated to learning and its process. He once stated, "It is not knowledge, but the act of learning, not possession, but the act of getting there, which grants the greatest enjoyment." This is a great way to live your life, really, to enjoy the process, and that product is just a little bonus. He invented many a thing, but the thing that we are going to remember him most for is this wonderful Gaussian curve that we love so much. And now we have this lovely lady, which I admit before I even start, she is not directly related to what we're learning about, but there are not very many females in our historical moments, so I put them in as much as possible whenever I find an interesting one. So initially, our friend Gauss from the last historical moment just a moment ago was corresponding with an Auguste Antoine Leblanc, or Monsieur Leblanc for short. He was impressed by this person and kept up a correspondence for quite a while. But it turns out that Monsieur Leblanc was actually Sophia Hedman. She taught herself Latin, mathematics, and physics in a time when women were rarely educated or able to obtain an education, and she held her own by writing in this pseudonym, Monsieur Leblanc, to Gauss among many others. She was well respected by a handful of people, but of course, because of the time period, she was never fully acknowledged or honored for her work. So that's what we're doing it here. Long live Sophia Hedman. Let's get back to the normal distribution. The normal distribution, or the bell curve, or the Gaussian curve, whatever you'd like to call it, is a graphical representation of one variable's probability distribution. So let's get reacquainted. Let's look at height again in females. So I'm going to put height here on the x-axis in inches, because it makes our life easier. And remember that y-axis is that probability. So what if I asked, what is the probability that a woman is 5'11" or 59 inches? Or said another way, what percent of that population is 4'11"? So remember that proportions, which can be interpreted as probabilities, are just percentages in decimal form and range from 0 to 1 instead of 1 to 100%. So if we look real close, we look for our 59, people who are 4'11", and we're going to go over here and we're going to see that the probability is 0.03. Means there is a 3% chance that I select someone at random and they are 4'11", or said another way, 3% of the female population are about 4'11". Let's zoom out for a second and let's answer that question that you're probably screaming at your computer at this point, which is, why do I care? Why do we care about probability and distributions? Ugh. It can be incredibly helpful because much of life, and especially statistics, There is so much uncertainty due to sampling error, which we'll talk about, or due to measurement error, or just the nature of taking a sample when you're only taking a sample from that whole population. In statistics, we don't prove anything. Really, we just can provide evidence for and try to quantify some of the probability associated with seeing certain things. So how likely is it that you see a woman who's 4'11" or 6'2"? That might not be of much interest to you because it's a statistics example that is a little bit more lighthearted. But what about something like, how likely is it that Flint, Michigan water is or is not contaminated with lead? Or what's the probability or the likelihood of UT having in-person classes? What's the probability or the likelihood that you catch COVID-19? And how likely is it that you make an A in this class? Things like the normal distribution can help us quantify some of this uncertainty, and that is very powerful. So, to be able to do all that fun stuff I just said, we gotta do some more translating of those numbers. We got to do something called standardizing. So, translations again. I use this phrasing because I think it's a good way to explain how we go from one set of numbers to the next, but they're all related. So here is that lovely normal distribution depicting women's heights, but what if I want to see the distribution of some other variable? Or what if I really don't care about your actual height, but I want to know how tall or how short you are relative to other people? How do we reduce it down or translate it to just the important bits of information? With standardizing, with the z-scale. We can take any scale and transform it into a simplified standard scale, in this case called the z-scale. A z-score tells you how many standard deviations a person's score is away from the mean. The z-scale and the z-scores associated with it allow us to make comparisons across different scales, like different tests, and different situations. So if we go and look at our lovely curve again, there was a lot of other stuff down here that I hadn't addressed yet. If we look down right here, we have z-scores. So the z-scale, or z-scores, has a mean of 0, which is right in the middle, and a standard deviation of 1. This is very useful to us because we can take any normally distributed variable like height, intelligence, even measurement error, which we'll see later, and we can convert it into this standardized scale. And then we don't need to know all the details about whatever the original scale was. We can understand a standardized scale much better than we can understand your specific scale for whatever test it is that you gave out. So if we look again at this curve, we see our mean of 0 for our z-score. If we look at percentiles, we see 50th. What's the average of 1 through 100? 50. This is all the same way of saying dead in the middle, right in the middle. And that is our mean on this curve. Now they all look a little bit different, but again, this is all the same message, just said in a slightly different way. You might be wondering, why would you use one language over another? It depends on what you're trying to communicate, or it depends on what kind of statistics you're trying to run. So how do we actually go about taking a scale like height, intelligence, or SAT scores and turn it into that simplified, standardized z-score, z-scale? We need a few things. We need the mean, standard deviation, and the score of interest. In other words, the person's score that you want to translate. Z-scores are standardized standard deviations, and you can kind of think of them as the units of standard deviations. The scale or the language of standard deviance. So remember, when you divide anything by something, so here we're dividing by standard deviation, we're translating all those numbers into the language of standard deviations. So here, notice that here are our z-scores. We go from 0, 1, 2, 3, and the same but negative. And notice here we have standard deviations. And we have 1 times standard deviation, 2 times standard deviation, 3 times standard deviation, and so on. So they correspond to each other, but again, the z-score is like the totally reduced down version of that language or message. It doesn't have any extra fluff or any additional information from the scale. It is like drilled down to its most important unit, the standardized unit. Now let's actually practice and convert some raw scores into z-scores. So here are some SAT scores, and maybe you took the SAT recently, but do you know what any of these scores mean? Do you know if any of them are particularly good or bad? I mean, I think that one's pretty good. I think that one's kind of bad, but beyond that, I don't really know, because I don't remember the scale and the scores for SAT. It's been a while for me. So let's translate them into z-scores, and then they can be more interpretable. So let's convert our first score. We have our first person here with a 1555, and the average for everybody is 1,000. So we're going to subtract 1,000 from 1555, and we're going to divide that by the standard deviation. Remember, standard deviation is how much people on average differ from each other. So in the SAT, the average amount of difference for most people is about 210 points. Now if we do that calculation, we end up with a z-score of 2.64. Ta-da! Now let's use some editing magic and fill in the rest of the answers. Bam! So here we have the rest of our z-scores. Now they might not mean much to you yet, but let's just step back and think about it. Knowing what you know now, what would a z-score of -3 mean to you? Would that be really good or really bad? Let's remember real quick, what is the average of the z-score scale? What's right in the middle? Value of 0. So if you have a -3, that's probably kind of bad. If you have a +3, that's probably pretty good. If you saw a score of -3 without even knowing the original scale, you would know that person was way below average. In this case, they would have an SAT score of 370, which is incredibly low. It's so low that it's actually lower than the possible value you can get on an SAT. But now, I hope that you can see that just knowing the z-score can let you know a lot more than knowing that somebody had a, I don't know, 1270. I don't know, is that good? Is that bad? It's a 1.29. So we know that they're quite a bit above the average, and that's actually quite good. So here I've taken the SAT data and the standardized z-scale, and I've put them on our lovely curve. So our mean for our SAT scores was 1,000. That would correspond to a z-score of 0. Now we have our standard deviation here, 210. I can translate our z-score values and our raw score values back and forth so I can find what's the corresponding value for a z-score of 1. That would be an SAT score of 1210. A z-score of 2, corresponding SAT score of 1420. Now remember, these curves are all probability curves. We can technically look up the probability of seeing somebody with a score of 1210. So I took all those z-scores that we calculated from our SAT data, and I just mapped each one of those data points onto this curve. So we have 3 people who were pretty close to that 1,000 average. We have somebody who didn't do too hot over here, that person who got a 585. They had a z-score of -1.98, which is very, very close to that -2. This person did amazingly well. They had a 1555, and that corresponds to a z-score of 2.64. Now I know this is all new, but you can hopefully already start seeing that z-scores that are pretty close to 0, just your average Joe, not too bad, not too good, most people are going to be here. But sometimes you'll see a z-score of like -2 or -3, or a z-score of +2, +3. Those are the people that are way out here. Those are much more rare. We can eventually, we'll see, we can figure out just how rare or how common one of those z values is when we can go and look up the probability later. That's coming. So translating back and forth, I've showed you how to calculate a z-score from a raw score. The raw score is the x, the mean of the population divided by the standard deviation of the population gives you that z-score. But you can figure out any one of these 4 variables by just rearranging them algebraically. Now, if instead of trying to memorize all of these different equations, I would suggest just learning the one and just playing around algebraically and trying to solve for each different variable. All right, we've arrived to our 68, 95, 99 rule. What on earth does that mean? Let's find out. So how many in the curve? If we look at this, There are even more numbers in here that I've been ignoring. We have this 34.13 thing. What on earth is that? That is the proportion of people, the percentage of people that are between 0 and 1 standard deviations. Here we are again with our curve. Notice these percentages. This tells us what percent of the observations, people, fall within this range. So from a z-score of 0, so the average, to a z-score of positive 1, there are about 34% of people that'll get a score in between there. In our SAT example, that means that 34% of SAT test takers will have a score somewhere between 1,000 and 1210, 1 standard deviation. We can also see that really extreme z-scores, like a positive 2 or positive 2.5, they're going to be way over here, and the amount of people who have z-scores in that range, much smaller percentage. And again, it's like somebody getting a 1555 on the SAT or that 580 on the SAT. So really, really high or really, really low, very few people score that high or that low. Normally distributed data has a really nifty little rule associated with it. So let's notice here that a z-score, let's say of -1, would be right here, and over here would be a z-score of positive 1. The amount of people that will score between -1 and positive 1 is about 68%. Now, what about 2 standard deviations, plus and minus? That would be like right here, and that is about 95% of people. 95% of people will have scores between -2 and positive 2 z-scores. Then if we go all the way out to -3 and positive 3, 99.7% of people will fall between a z-score of -3 to positive 3. So these are pretty nifty, and I suggest you familiarizing yourself with the 68, 95, 99 rule. Let's look at this 96, 95, 99 rule with our SAT data. So what are the 2 SAT values that are associated with a -1 and a positive 1 z-score? Basically 68% of people score between what and what on the SAT. If you do a little bit of math magic, you get 790 to 1210. 68% of people will have a score between 790 and 1210. If we want to do 95%, z-score of -2 and positive 2, that would be 580 and 1420. So 95% of all SAT test takers are going to score between 580 and 1420. Now you might be wondering about that 99.7% part with the -3 and positive 3 z-score. Well, you can translate those numbers and it would be 370 to 1630. But the SAT only goes to 400 and 1600, so it's a little bit tweaked. So let's look at the proportions in each one of these little slivers. You might notice now we have a 4. They can keep going. It's just that most data is going to fall between plus or minus 2 or 3, so we usually just stay there. But they're out there. The probability is there. It's just incredibly small. So if you wanted to know the proportion of people that would get a z-score of positive 3 to positive 4, somewhere in this little realm, it would be 0.1%. And then from here, from positive 2 to positive 3, it would be about 2% of people. Then here, from 1 to positive 2, it'd be about 13–14% of people. And then from 0 to 1, it would be 34% of people. And the same is true if you were to do it negative on the other side. We can also look at this cumulatively. So if I wanted to know what percent of people fall between this -4 to our z-score of 0, what would that be? Knowing what you know about the average and how it cuts the data right in half for normally distributed data, that means that this chunk here, this hole from the middle all the way over here, that's about 50%. Now if we want to know, for example, how many people score a z-score of 1 or below, that would be 64% of people. See where I'm getting that? That I would look for right here, a positive 1 z-score, that would be right here, and I would just add up all these values down here, and it would be about 84%. So now we're going to look at the association between z-scores, percentiles, and probability. This is the unit table that I just mentioned, and though it doesn't seem like it, it's actually pretty cool. You can take any z-score that you calculate, so you translate the raw score into a z-score, and you can look up that z-score and figure out what percent of people scored above that or scored below that. This is also how you get the percentile score. So if you think back to any standardized test that you've taken, I'm sorry, America, we're all about standardized testings, like your SAT or ACT, there was probably a percentile score associated with that. And a percentile score is letting you know that if you were in the 90th percentile, you scored better than 90% of people. So for example, the percentile of someone who scored a 1035 on the SAT would be a z-score of 0.17. And we know that that's pretty close to the middle, right? And it's positive, so it's going to be a little bit more than 50%. And it would be a proportion of 0.5675. This means that about 57% of test takers scored below this one person. Now, if you have a z-score of 0.25, what is your percentile rank? Or a z-score of 0.0, or a z-score of 0.49. Now, one of these is very quick, and you don't even have to look anything up. Come on, use that intuition. Which one is it? 1, 2, 3. This one! This one's actually a gimme. What is it? Well, it would be your percentile rank if you got exactly the average. If you were exactly a z-score of 0, it would just be 50th percentile. But let's look up the other two. So a z-score of 0.25 corresponds to the 60th percentile, a z-score of 0.0 corresponds to 50th percentile, and a z-score of 0.49 corresponds to the 69th percentile. It's equivalent to saying that 69% of people scored below you. Now I can ask this a slightly different way and say, what percent scored above you if you had a z-score of 0.49? And you can look that up, and it would be about 35%. What percent scored above you if you had a z-score of 0.25? Here is that 0.25. And instead of looking in the body, because we don't want the body, we technically now want that little tail. So we look at this value, and it's about 40%. So about 40% of people did better than you. So if I randomly select someone, what is the probability that they scored above you if you had a z-score of 0.49? You can say 31%. Now this notation here, this is how you would write probability of z-score greater than 0.49. And I will use some of this notation throughout the rest of the course. The next one, what is the probability of a z-score greater than 0.25? It's the same as saying if you had a z-score of 0.25, what percent of people scored above you? About 40%. So far, I've been showing you how you can look up the probability of things, and we can also quickly now see that if somebody had a z-score of 0.01, they are very close to the average. If someone had a z-score of +3, we know that they are well above the average. But the other really cool thing you can do with standardized z-scores is compare across different types of scales. So here's an example. 2 different students in 2 different classes. There are 2 different instructors teaching statistical literacy. A student in Z's class had a score of 45 on the first exam, and a student in D's class assigned a different exam had a score of 50. So who did better? Now you might be tempted to think, well, obviously, the second student, he got a 50 instead of a 45. But we don't know the original scale of the test. Maybe the test was out of 100 or the test was out of 70. We don't know. And we're asking who did better between the 2 relative to each other. So we have to do some translating. Let's do it. So now here we have the information that we need. So in Z's exam, the mean was 40, standard deviation of 5, student score 45. In D's exam, the average was 55, standard deviation of 5, student of interest had a score of 50. Now let's translate. Ta-da! Now we can actually compare them. We can easily see that student in Z's class had a z-score of +1 and student in D's class had a -1. Now we can easily compare them without having to worry about what the original scale of the exam was. We know that Z did better. This is a real-world example of how percentiles can be incredibly useful. When you know that the average is a certain value, you can kind of figure out when somebody's really above that or really below that. And the really below is of great interest to speech language pathologists, for example. This test is to be given to children to check for language and speech problems, because if a child is having trouble learning to speak or learning to talk or processing language, they need to have some sort of therapy or services administered as early as possible. But how severe is severe enough? Now that you know how this curve works, most people are going to score here. Some will be really good, and we obviously don't have to worry about those. And here we have still maybe not terrible concern, but when we start getting into below average, moderate to severe, and then very severe, these are the people we have to worry about, because they're in the bottom here, bottom 2%, here about bottom 15%, and this is the range that people need services. So this is an example in the real world of how percentiles and the standardization can be immensely helpful. So again, why standardize? Translating raw data into standardized scales allows us to interpret any one person's score more deeply and relatively to other people. A z-score of +2 would tell you a person did very well, and you don't have to know anything about the raw score. A z-score of -2 on a language test would tell you this person may need some speech therapy and needs services. The conversion of data to have a mean of 0 with a standard deviation of 1 makes computations and interpretations easier. This type of translating of data is at the core of much of what we'll be doing for the rest of the semester. So why are we doing this again? Always trying to answer that question. Why do we care? Why are we doing this? We can take any scale and transform it into the simplified standard scale, the z-scale. The z-scale and the z-scores associated with it allow us to make comparisons across different scales and tests and situations. And we can use standardized z-scores to help us figure out the probability of things. This is a core concept in statistics. So up next, we move beyond one person's score and we start looking at standardized mean values and what those can tell us in probability of z-scores and z-tests. And I'll see you there. Yep, quick z-scores in R. Here we see the example of two different students in class. I assigned this value of 45, that was person Z's score. The mean of that exam was 40, the standard deviation was 5. To get a z-score, you take that value, that 45 person score, minus the mean divided by the standard deviation, and you'll get a z-score. Do the same for person in D's class, and you'll get both of the z-scores instead of having to do any of it by hand. Here is the example with the SAT scores, and I'm also showing you here how you can actually, instead of having to look up on that table, you can actually just ask R to tell you what the proportion is in that curve using p-norm. So that is the R for the day. Please watch the other videos that go into more detail. See you in the next one. Cheers!